Hello friends, I am Dr.Manisha, Assistant Professor, Department of Physics, KVN Naik College, Nasik. Welcome to my channel. Friends, if you have not yet subscribed my channel, please subscribe it. In this series of lecture, today we will study Bohr's atomic model. In previous video, we have seen Thomson's atomic model and Rutherford's atomic model in detail. Today we will start with Bohr's atomic model. Thomson's atomic model and Rutherford's atomic model failed to answer any questions related to the energy of an atom and its stability. In the year 1913, Niels Bohr proposed an atomic structure model describing an atom as a small positively charged nucleus surrounded by electrons and that travel in circular orbits around the positively charged nucleus as planets around the sun in our solar system, with the attraction provided by electrostatic forces, popularly known as Bohr's atomic model. It was basically an improved version of Rutherford's atomic model, overcoming its limitations. On most of the points, he is in agreement with him, like concepts of nucleus and electrons orbiting it. Salient features of Bohr's atomic model are: electrons revolve around the nucleus in the stable orbit without emission of radiant energy. Each orbit has a definite energy and is called as energy shell or energy level. An orbit or the energy level is designated as K, L, M, N shells. When the electron is in the lowest energy level, it is said to be in the ground state. An electron emits or absorbs energy when it jumps from one orbit to another. When it jumps from higher energy level to the lower energy level, it emits energy while it absorbs energy when it jumps from lower energy level to higher energy level. The energy absorbed or emitted is equal to the difference between the energies of the two energy levels and is determined by the Planck's equation. Delta E is equal to E2 minus E1 is equal to h nu, where h is the Planck's constant and nu is the frequency of electromagnetic radiation emitted or absorbed, and delta E is the energy absorbed or emitted. The angular momentum of an electron revolving in the energy shell is given as mvr is equal to n into h upon 2 pi, where n is the number of corresponding energy shells which are equal to 1, 2, 3 and so on. Me is the mass of electron, v is the velocity, r is the radius and h is the Planck's constant. But this Bose atomic model theory is also having some limitations. It violates the Heisenberg's uncertainty principle. The Bohr atomic model theory considers electrons to have both the known radius and orbit, that is, known position and momentum at the same time, which is impossible according to Heisenberg. The Bohr atomic model theory made correct predictions for smaller sized atoms like hydrogen, but poor spectral predictions are obtained when the larger atoms are considered. It failed to explain the Zeeman effect when the spectral lines is split into several components in the presence of the magnetic field. It failed to explain the Stark effect also, when the spectral lines get split up into fine lines in the presence of the electric field. Now we'll study about this atomic spectra. It includes emission line spectrum and absorption line spectrum. Rainbows are one of the most beautiful things on earth, containing the spread of colors that our eyes can see. That is why we use the expression every color of the rainbow. But did you know this expression is not technically true? That the rainbow is actually missing a few colors. If you could look extremely closely at the rainbow and analyze its light, you would find dark gaps in the otherwise continuous spectrum of light. This is because pure white light can be shined through a prism and split into every color our eyes can see. But the sun does not send us pure white light. It sends us an atomic spectrum. An atomic spectrum is a spectrum that has been shined through or originates from the material, usually gas, and contains patterns that are characteristics of the elements present in the material. When we analyze the sun spectrum, for example, we can figure out what elements are present in the sun. The emission spectrum of the gas is represented by the collection of separate colored lines with dark spaces between them. The lines are the parts of the spectrum where the emission occurs and the photons are emitted, while the dark spaces are the parts where there is no emission, hence the darkness. The difference in colors is due to the variation of the energy levels of the electrons. In case of the ionic solution, the spectrum will consist of discrete color bands instead of lines, since the substance here is compound with the different atoms which together produce complex colors. Emission spectrum is different for the different elements subjected to the same source of energy due to the difference in the excited energies of the different electrons of the substances. This is why the light emitted by each substance is different. The frequency of the emission spectrum are frequencies of light that are dependent on the energy of the emission. The energy of the photons emitted is related to its frequency by the formula E is equal to h nu, where E is the energy of the photons and h is the Planck's constant. Nu is the frequency of the photon. This shows that the frequency of the photon is directly proportional to its energy. Emission spectra can be divided into two, line spectrum and continuous spectrum. When the spectrum appears as a series of lines which is separated by black spaces, it is called as line spectrum. And when the spectrum consists of wide ranges of colors in a particular wavelength range or interval, it is called as continuous spectrum. Now, absorption line spectra. It consists of two types of spectrum. First is atomic absorption spectrum and other is molecular absorption spectrum. The absorption spectrum of an element is represented by the continuous bands of colors with separate dark lines between them. The entire band represents the total light that is focused on the element, and the dark lines are the parts of the spectrum where the electrons absorb light photons. Hence, there is absence of light at these parts. The remaining colored parts of the spectrum represents the part of the incident light that has not been absorbed and hence appear as a wavelength specific colors. The reason for this pattern is that all the electrons of an atom are at the different energy levels at any given time. The energy difference between the two energy levels of each electron is different. When the light of any wavelength is focused on these atoms, each electron will absorb only that photon with the same energy as this energy difference. The rest of the photons are not absorbed, that is, these photons are scattered. The dark lines corresponds to the same position where the colored lines of the atoms emission spectrum would occur. Absorption spectra can be measured with the frequency, wavelength and the wave number. There are two types of the absorption spectra. The atomic absorption spectrum is the spectrum obtained when the free atoms, that is generally gases, absorb the wavelength of light, and the molecular absorption spectrum on the other hand is the spectrum that is seen when the molecules of the substance absorb wavelength of the energy, generally ultraviolet or the visible light. Now we'll see the uses of atomic spectra in detail. When the atoms are excited, they emit light of the certain wavelengths which corresponds to the different colors. The emitted light can be absorbed as the series of colored lines with the dark spaces in between. This series of colored lines is called as line or the atomic spectra. Each element produces a unique set of spectral lines. Since no element emit the same spectral lines, the elements can be identified by their line spectrum. Friends, in the next video, we will see about the classical planetary model of hydrogen atom. I hope you like this video and don't forget to subscribe my channel and hit the like button. Thank you.